All right, we are on to questions 3 and 4 for 2016. Let's go ahead and jump into it. So we're on to Calc inactive problems. Number 3, we're given a graph. All right. So it says the figure above shows the graph of the piecewise linear function for -4 to 12, and the function g is defined by, g is defined by an integral of 2 to x. So we're going to go ahead and make a note that g prime of x is equal to f of x by ftc part 1. So the fundamental theorem of calculus part 1. So this graph given right here is the same thing as g prime. So I think that's always a helpful thing to recognize at the beginning of these problems. And A says, does g have a relative minimum, a relative maximum, or neither at x equals 10, and justify your answer? All right, so we're talking about g here. And if I look right here, that's saying that g prime of 10 is equal to 0. That makes it a critical point. But is it changing directions? No, it's going negative to negative. So since it's not changing from positive to negative or vice versa, it's not going to be a max or a min by the first derivative test. Okay, so I'm going to say neither. I'm going to say neither at x equals 10. And the reason is because I'm going to say at x equals 10, g prime, which is equal to f by ftc part 1, goes from negative to negative, therefore being neither max or min. If you want to get fancy, you can say by the first derivative test. Okay, so it's neither at x equals 10 because at x equals 10, g prime equals f by ftc part 1 goes from negative to negative, therefore being neither max nor min by the first derivative test. I'm sure there's a cleaner way of stating that, but I think that's pretty good. Okay, had to change from positive to negative or vice versa. And remember, we always justify our answer in terms of the graph given. So notice how I justified it in terms of g prime, okay, or f, and I stated that connection by ftc part 1. Okay, all right. Let's go on to question 3. It says the figure above, or B, does the graph of g have a point of inflection? A point of inflection at x equals 4, and justify your answer. All right, let's go ahead and justify our answer. Okay, we have a point of inflection whenever the derivative is going from increasing to decreasing or vice versa. So look at x equals 4. X equals 4 here. The graph of g prime does go from increasing to decreasing, therefore making it a point of inflection by definition. So I'm going to say yes. Okay, and here's the reason why. Since g prime, which is equal to f by ftc part 1, goes from increasing to decreasing at x equals 4, then g has a point of inflection at x equals 4. So since g prime equals f by, so since g prime goes from increasing to decreasing at x equals 4, then g has a point of inflection at x equals 4. That's just a definition of a point of inflection. Point of inflection occurs when the derivative goes from increasing to decreasing or vice versa. All right? Not too bad, not too bad. Let's move on to C. C says find the absolute minimum value and the absolute maximum value. So we are talking about absolute extremis here, both absolute min and absolute max value of g on the interval -4 to 12, so over this entire thing. Okay, and justify your answer. All right, so this is what I'm going to say for my justification here. I'm going to say that absolute extrema occurs at critical points, and I'm going to specify here critical points that change from positive to negative or negative to positive. Okay, because we do have a critical point at 2 and 10, but I'm not going to consider those points because we're not changing direction, so they're not going to be a max or a min. So absolute extrema occurs at critical points that change from positive negative or negative positive, or endpoints. So we're going to check all these points. Okay, and I'm going to check them in my little chart here. So I'm going to say, all right, here's my x value, here's my y value. Now my endpoints, I'm going to go left to right here. The points that I'm checking, I'm going to do it in red, are at -4, -2, at 6, and at 12. Because -4 and 12 are my endpoints, and -2 and 6 are critical points where they change direction. So I'm going to check -4, -2, 6, and 12. All right. Now, checking -4. So remember how we're going to figure out what these values are. Our function g of x is defined by the integral starting from 2 to any x value. So we're starting here. So if I'm trying to figure out the value of, say, -4, which is right here, that's going to be this area right here. Okay. And remember what happens is that this negative area and this area right here, those cancel each other out. So I'm left with just whatever the area of that triangle is. And because we're going backwards, it's going to make it negative or change the sign. So originally, that's going to be a triangle that's 2 by 4. 8 divided by 2 is 4. So originally, that would be 4, but moving backwards makes it -4. So that's the area of that. Okay. Now, if I'm trying to figure out the value of -2, that's going to be this area right here. Okay. Which, if I take the area of that triangle above the x-axis, that triangle is a 4 by 4 triangle. So I'm going to go 4 by 4 divided by 2, which is 8. But because we're moving backwards, it's going to make that 8 negative. Okay. Then I'm also going to figure out the value of 6 by taking the area under the curve from 2 all the way to 6, which is the same area as the previous triangle, but because I'm moving in the right direction, it's going to make it a +8. Okay, so that's +8. And then lastly, I'm going to go to 12, which is the area of the blue triangle, the area of this triangle, which those actually cancel each other out, and then finally the area of this little triangle here. And because I'm moving forward and it's below the y-axis, that's going to be a negative area. And it's actually going to be negative, let's see, it's 2 by 4 divided by 2 is -4. Okay. So, looking at all my extremas, all my possible points of absolute extrema, I have a maximum, an absolute maximum at 0.6 and an absolute minimum at -8. So you probably want to specify that a little bit, but I'm going to say, just point to the chart and say this is my absolute minimum and this is my absolute maximum. There you have it. That's how you do it. So we talked about the points that we were going to consider, and we considered all those points, and we figured out which ones was the smallest and the biggest. So yay, not too bad. And then lastly, D says for -4 to 12, so this whole interval, find all the intervals on which the value of G, which again was this equation here, is less than 0. Okay, so let's start off at 2. Go backwards and forwards and just figure out the intervals. So if I go backwards, remember what we said, this is a negative area, so that's negative area. like we figured out the value of -2 in the previous problem, right? The value of back to -2 is equal to -4. We figured out that value, or I'm sorry, -8. We figured out that value in the previous problem. If I go all the way down to right here, it's going to be -4. Okay, so moving backwards from 2 all the way to -4, that whole interval is always going to be negative. So that's always going to be true. So one of my intervals is from -4 to 2. That whole area is going to be negative. What about if I move right? If I move to the right, this is going to be a positive area. This is going to keep being positive. That's actually going to cancel it out. So that goes from positive to 0. And then it starts to become a negative area once I go past 10. Okay? So the other interval in which g is negative is 10 to 12. Okay? That's it. Again, that's pretty much just using how we found our answers in C and just kind of rewriting it down. So we had negative areas from -4 to 2 and a positive, or a negative area from 10 to 12. The only positive area we had was on this interval here. Okay. All right, cool. That was 3. So let's see. Look at this. Look what we got a point for. Somewhere in A, B, C, or D stating the fact that g prime of x equals f of x. They didn't state by f of tc part 1, but we get a point for stating it. So I always state it at the very beginning and anytime we use it. All right. So you could have gotten it in part A, but we just got to answer with justification. So we said that it was neither because it never changed signs. For B, we get a point for just the answer again, right? Which was the fact that it was yes because it goes from increasing to decreasing at 4. And then C, we got 4 points for C, so it's very important. The fact that we considered -2 and 6 as critical points. The fact that we considered our endpoints. So we got 2 points, half the points for considering all the points. And then 2 points with my answer with justification, which is the fact that it's -8 for my maximum, or I'm sorry, my minimum, and 8 for my maximum. So there you have it. And then D, we just get 2 points for that interval, probably 1 for each. So I don't think that was the worst problem in the world. I like doing problems like that. I'm really hoping that y'all get one like that. Okay. All right, let's move on to 4. 4 is literally just giving you a differential equation. 4 is giving you a differential equation. Now I warn y'all with this problem here, I had to do a lot of writing, so hopefully I can write it nice and clear for y'all and we have good discussion. We'll see what happens. It says consider the differential equation as dy over dx equals x squared minus 1/2 y. Cool. Let's find the second derivative. So we're just going to find the derivative of this in terms of x and y, which we've done this plenty of times. So this is equal to, so let's see, so d2y over dx squared is equal to 2x minus 1/2 dy over dx when I take the derivative. And when I plug in dy over dx back into it, I get 2x minus 1/2 times x squared minus 1/2 y, which leaving your answer like that is completely fine, but I distributed the 1/2 for the heck of it and said it was 2x minus 1/2 x squared plus 1/4 y. All right, there you have it. That's the answer to part A. All we did was find the second derivative. So, yay, good job. Okay. Now keep this derivative in mind. All right, keep that second derivative. So we got the second derivative and we got the first derivative. So keep both of those in mind. B says, let y equal f of x be a particular solution. So we got some solution to this differential equation whose graph passes through the point -2,8. So I got -2,8 is on my function. And it says, does the graph of f have a relative min, a relative max, or neither at the point -2,8? Now, to figure out if we have a max or min, we have 2 tests we can do. We have the first derivative test and the second derivative test. Now, with differentiable equations, when we have both x and y points in there, I think the better test to use is the second derivative test, especially because we have the second derivative we found in part A. So my justification here is going to be the second derivative test. And again, guys, I would always use the second derivative test, especially if you have both of them, and especially if it's a differential equation with x and y. If you try to do the first derivative test and had to figure out points to the left and right of your critical points, well, you still have a y to consider, and that kind of confuses things. Okay. So second derivative test states, first of all, we're going to look at the first derivative and make sure that the derivative is indeed 0, because it has to be a critical point for it to be a max or min. So I'm going to say dy over dx of the point negative 2, 8 is equal to, that's negative 2 squared minus 1/2 times 8, which is equal to 4 minus 4, or 0. So it is a critical point. That's good. Now, it all depends on what the sign is for the second derivative. That's going to tell us if it's a max or min. So I'm going to do d2y over dx squared of negative 2, 8. And we got that formula from before. So remember, that's going to be, just looking at before, it's going to be 2 times negative 2 minus 1/2 negative 2 squared, and then plus 1/4 y, or 1/4 8. Which this comes out to be actually negative 4, which is less than 0. So by the second derivative test, that means that negative 2, 8 is a relative, it's concave down, which makes it a relative maximum. All right, that's just by the second derivative test. Okay. All right, so good job on that. All right, let's move on to the C. C says, all right, now I got g of x as a particular solution to the differential equation, and that contains the point negative 2, or negative 1, 2. And I want to find the limit of negative 1, the limit as x approaches negative 1 of this. Show the work that leads to your answer. So this is the one I wrote a lot on, and it's because I really want to make sure that we write the correct work for these types of problems. A lot of times when you're doing limits as a part of a problem like this, you already know what this is leading to. It's probably going to be L'Hopital's. Okay, so let's make sure. So the correct notation for this is I want to talk about the limit of the top and the limit of the bottom. So I'm going to do the limit as x approaches negative 1 of g of x minus 2. All right, so if I plug negative 1 into that, g of negative 1, so it's g of negative 1 minus 2, which is actually equal to 0, because it's 2 minus 2 is 0. If I do it for the bottom, if I say the limit as x approaches negative 1 of 3x plus 1 squared, if I plug negative 1 into that, I also get 0. So it's 0 divided by 0, which means we have to do L'Hopital's. So I'm going to say by L'Hopital's, I'm going to say that the limit as x approaches negative 1 of g of x minus 2 over 3x plus 1 squared equals. So that's the long part, is the fact that you're supposed to write the previous limit and say by L'Hopital's that limit is actually equal to, and then you take the derivative of the top and the bottom. This is equal to the limit as x is approaching negative 1 of g, the derivative of the top is just going to be g prime of x over, and then the derivative of the bottom is just going to be 6 times x plus 1. Okay. Then you plug negative 1 into that. So we're going to consider the limits of the top and the bottom again. So I'm going to say, all right, okay, well then the limit, so just like I did before, I'm going to do the limit as x approaches negative 1 of g prime of negative 1. Which if I do g prime of negative 1, if I plug negative 1 into that, I'm plugging into this function up here. So that's negative 1 squared minus 1/2. And then the y value again was 2. We got that from right here, times 2. And unfortunately, that equals 0. So hopefully the bottom part doesn't equal 0, but it does. So that's the limit as x is approaching negative 1 of 6 times x plus 1. which if I plug -1 into that is equal to 0. So again, taking the derivative didn't work out for me because it did. It's going to, but it's 0 over 0 again, so I have to do L'Hopital's one more time. And you might have to do it more than that, but I'll go ahead and tell you it's just one more time. So now what I have is, okay, I'm going to say it again. By L'Hopital, okay, I'm going to say that the limit of what I had before, x approaches -1 of g prime of x over 6 times x plus 1 is going to be equal, and I can do the derivative again, is going to be equal to the limit as x approaches -1 of g double prime now is the derivative of g prime over the derivative of 6x plus 1 is just going to be 6. Okay. Now, if I were to, and I'm going to tell you this works out, so if I go ahead and plug -1 into that, so g double prime of -1, well, I got that formula from part A, so g double prime of -1, where did I write that down, is going to be equal to -1 squared minus 1/2 times, wait a minute, so I wrote that down wrong, sorry. I was writing down the last part again, sorry. So g double prime of -1 is equal to 2 times -1, and again I'm using the formula from part A, minus 1/2 -1 squared plus 1/4 times 2 all over 6, which equals -2 over 6 or negative, oh, you can't see that anymore, sorry, -2 over 6 or -1/3. Okay, and that's the final answer there. Yeah, so we had to do L'Hopital's twice, which kind of sucked, but I just wanted to make sure we write the correct way of L'Hopital, so I'm glad this problem came up. Remember, you have to discuss them as the individual limits on top and on bottom, and if they're both 0 or both infinity or negative infinity, then you can say by L'Hopital's, and you want to make the statement that the previous limit is equal to this new limit, the derivative of the top divided by the derivative of the bottom. Notice how we had to do the limit of the top and bottom again, and then I was able to do L'Hopital's one more time, and it worked out. Okay, so I usually do pretty well with L'Hopital's. I'm not worried about that one. All right, let's move on to the last one now. D. D says, let now h of x be the particular solution, and we have a new initial condition. It's that h of 0 is equal to 2. And we're going to use Euler's method, starting at x equals 0 with 2 step sizes of equal sizes to approximate h of 1. All right, Euler's method. Doesn't hurt to go ahead and just write down the formula for Euler's method. Remember, we said it was yn plus 1 equals, and it's the derivative of my current spot. So dx over dy over dx of my point x comma y times my step delta x, and then plus my previous y value y sub n. Okay, that's Euler's method. And 2 step sizes is pretty doable here, right? Remember how we set it up in a chart? We'll set it up like this. I'm going to say, all right, we got the point 0,2 initially. Now, I'm doing steps of equal size to get to 1, so that's got to be step sizes of 0.5. So that's going to be 0.5 comma something, and then 1 comma something, my answer. Okay, that's 2 steps of equal size approximating h of 1. So let's start off with finding this first y value at 0.5. That's going to be, I'm going to say yn plus 1 equals. So the derivative of my current point, I got the formula for my derivative up here, is going to be equivalent to 0 squared minus 1/2 times 2, okay, times my delta x, which is 0.5, my change in x, that's always the same, and then plus my previous y value of 2, okay. This is equivalent to, I think that's -1 times 0.5 plus 2. And that equals 3, let's see, that's -0.5 plus 2, or 1.5, or 3/2. So this right here is 3/2. So now we're going to do the same process to find the point at the approximation at 1. We're going to say y now maybe n plus 2 is equal to. How does it do that? It's very annoying. The point we're going to use is 0.53 now. So I'm going to do x squared, or 0.5 squared, okay, minus 1/2 times y, which is 3/2, times my delta x, 0.5, and then plus my previous y value, 3/2. Now I realize this problem's calc inactive, but I think they would like for you to simplify that out. So we're going to do that. Okay, 0.5 squared minus 1/2 times 3/2. That's going to be, try to do it plenty of steps here. It's 0.25 minus 3/4 times 0.5 plus 3/2. Okay, which if I simplify that out, 0.25, that's 1/4 minus 3/4 is -1/2, right? Yeah, so -1/2 times 1/2 plus 3/2. That's equal to -1/4 plus 3/2, which I'm going to go ahead and say is 6/4. So my final answer is going to be 5/4. So the approximation for 1 is approximately 5/4, or 1.25. Euler's method. There you go. All right. So here's my answer key. I got the second derivative in terms of x and y. You see that right there. For B, you get 2 points with the conclusion with justification. And so did they used the second derivative test. They did the first derivative to show it equals 0, and the second derivative to show the point was less than 0, so therefore it's a maximum. Okay. Part C, you get 2 points for doing L'Hopital's. I would assume that's a point for each time you did it. So here and here. And then a 1 point for the answer, which is -1/3. Okay. And then D was the fact that we knew to do Euler's method and that we got the approximation to be 5/4. They did part D with more notation than anything. We did a lot of the work. We showed a lot of the work in a chart. So either way is fine. And that's questions 3 and 4 for 2016. And we're about to do questions 5 and 6 here shortly as well. So good luck.